Okay, so uh, we were looking at attack on RSA crypto system, and I think this topic is quite vast. So I think you can look at a lot of algorithms. So last class we looked at the primality testing algorithm, but I have not told you about the famous algorithm, which is by uh, Neeraj Kayal, Nitin Saxena, and Mahender Agrawal. But anyway, uh, today I'm going to do two factoring algorithms. In fact, some results I'll mention without any proof, and two algorithms, which were there earlier. People try to factor. I mean, there were certain cases they've used these algorithms, some of these algorithms to factor, integer using a distributed set of computers and so on, and they were able to, small cases they were able to handle, So that is a trick. Uh, but certainly, if you are very much interested in algorithms and want to look at more complexity of these algorithms. So I'm going to just mention about the complexity of the algorithm, because then otherwise, each algorithm if we teach, it will take a lot of time. So I think, so these two algorithms. And how many of you know about continued fraction? Have you heard of continued fraction? Continued fraction is I mean, people teach it in high school, right? 1 divided by 2 divided by 3 divided by 4 and so on, Or remember something like this, 1 by 2 plus something, 1 by 2 plus 3 by 4 or something, keep on doing, right? That has some connection with the some of these algorithms, right? So it's an interesting thing. So of course, I'm not going to do everything, but I'll give you some idea about it. So, so that I think we can finish the RSA crypto system. So next class, we are going to look at uh, discrete logarithmic problem, and discrete log problem and how things are done there. And after that, we'll talk about elliptic curves. By the way, there is also one important elliptic curve based algorithm for factoring integers. Lenstra was the main person who has done a lot of work in that area. So there is a lot of really work that you can look at it if you really want to learn these things. So a lot of stuff is there, but we are going to pick up only few of them, and some of the results I'm going to mention actually. So as you know, this is the general thing. If we know n, that means certainly we know phi of n. We can compute phi of n, right? Euler-Torsion function. And once we know n and phi n, and I want to find p and q, because we know that p into q is equal to n, then that can be done if we solve this equation, x square minus n times phi n plus 1 plus x plus n. So plug in the value of n and phi n and n here. So we get this equation. And then if we solve the equation, then we can factor, right? So that is the key thing. So we can find P and Q easily from this. Obviously, how hard it will be, that's another challenge. So let me give you first two results which are there. So first of all, one is a result that first result. Suppose n is a product of two prime numbers P and Q, and suppose this n has m digits. Okay, m digits are known. So if we know, I mean, so there are m digits of n. If we know somehow, right, first m by 4 digits or the last m by 4 digits of p, we can easily factor. And that is first result. So if the number n has m digits, somehow if you know the first m by 4 digits or the last m by 4 digits of p, then we can factor the rest of the thing easily. Obviously it requires a proof, understanding, but I'm skipping all those things because this is your first course in cryptography anyway. But this is a something interesting result. Another result that I am going to mention. Okay, so suppose n comma e is an RSA public key. N and E is a RSA public key, right? And again, n has m digits. Okay. If D is a decryption exponent, okay. And again, if we have at least the last m by 4 digits of D, then we can find D in time, linear in E log 2 base E. Okay, so if n and E is a RSA public key, RSA public key, and n has m digits, and D is the decryption exponent. So if we have at least the last m by 4 digits of D, then we can find D in time linear in E log 2E. This is another result, but of course without any proof. So you need to bear with me. So now I am going to give you a little bit of summary of what are the popular practical algorithms which people have used actually, factoring algorithms. I think it will take some time for me to write it here because anyway. One very popular is quadratic sieve. So this algorithm, the complexity is big O of e raised to 1 plus O of 1 square root of log n log of log n. Now log n is a natural base e, right? That is a complexity for quadratic sieve. We have elliptic curve, factoring algorithm, and that has complexity big O of two log p log p. Okay, and we have number field sieve. So basically these are the three ones almost. Okay, these are the three popular practical algorithms. Uh, but of course we are not touching any of them because you require a lot more mathematics to understand some of these things. So we go to the simple algorithms which are used. The first one is Pollard P minus 1 algo. Okay, this was given in 1974. So it requires two inputs, integer n, which you want to factor, and a bound b. Of course, n should be odd here. That's the assumption. Odd integer. And a bound b, it's a kind of pre-specified bound. Bound b, okay. So algorithm goes like this: initialize a with 2, then for the loop j to 2 to b, do I think writing is very bad here, but A raised power j mod n. D is the GCD you compute between A minus 1 and n. If 1 is less than D is less than n, then return D. Else return failure. Okay, so two input n and b, n is a odd integer, b is a specified bound. Then we compute a, and then for this loop we keep on computing a raised to power j, and then you compute GCD of a minus 1 and n, and based on this condition of d, you return. Okay, so let me show you the working of this algorithm. Okay, suppose p is a prime divisor of n, and suppose q is less than or equal to this pre-specified bound b, then for every prime power q which divides p minus 1, you can say that p minus 1 divides p minus 1 divides factorial b. So at the end of the for loop in the algorithm, we will have 2 raised to power factorial b mod n. Since p divides n, this implies that a is congruent to 2 raised to factorial b mod p, but we know that 2 raised to power p minus 1 is congruent to 1 mod p. This implies that a is congruent to 1 mod p. Okay, I mean this is possible since p minus 1 divides factorial b. That condition we have used here. Of course, there are many conditions, but so this will imply that p divides a minus 1, but p divides n. This implies that p divides GCD of a minus 1, a minus 1 and n, which is nothing but d. So d is basically turns out to be divisor of n. Okay, so this is how you find, I mean, you can keep on doing this thing, and the complexity turns out to be big of all these things requires proof, which I am not doing any of these things. Log n whole square plus log n whole cube. Okay. So this was polar p minus 1 algorithm. It's a very old algorithm. Anyway, so another one which is which I like it kind of is Dixon's random square algorithm. Random square algorithm. So this is based on another. So all these algorithms based on a lot of assumptions. Suppose we can find x not congruent to plus minus y mod n. Two such numbers x and y. Okay. Such that x square is congruent to y square mod n. So suppose we can find two numbers x and y such that x is not congruent to plus minus y mod n, but x square is congruent to y square mod n. In that case, n will divide x minus y into x plus y, right? Because x square minus y square is multiple of n, right? So n divides this. But neither of x minus y or x plus y is divided by n. So this implies that GCD of x plus y comma n one factor is GCD of x plus y comma n, and another one is GCD of x minus y comma n. These are two non-trivial factors of n. So let me give you an example. Okay. So we know that 10 square is congruent to 32 square mod 77. So I want to factor 77. So GCD of 10 plus 32 and 77 is 7. Therefore, 7 is a factor of 77. Okay. This random square algorithm uses a technique known as factor base. What is factor base? B is a set of B smallest primes for appropriate value of B. So let us start with example. N is equal to 15770708441. So let B is equal to 6 and capital B is 2, 3, 5, 7, 11, 13. Okay. Then we have 8340934156 square is equal to 3 into 7 mod n. Other one is 12044942944 square congruent to 2 into 7 into 13 mod n. These are bigger calculations. Obviously, you will be lost after some time. And 27737000011 square is congruent to 2 into 3 into 13 mod n. If you multiply all the three equations, this, and this, right, we are going to get I'm just multiplying all of them and then taking a square. So ultimately you are going to get 950343578 whole square mod n. So you can see that using initial results, using factor base, I can actually extend this result. So now we are going to basically higher values, right? And then you again compute GCD. I'm just writing 950343578 minus 546 with 1577070 8441. This GCD turns out to be 115759. So basically, using this factor based method, we can actually go for finding higher values of such pairs and then just compute GCD to find the value. Okay. Okay, I think then the last one I am going to mention. low exponent attack. I think I can give you example. Okay, we are going to use the following result. Suppose P and Q are primes with Q less than P less than 2Q, and suppose N is equal to product of 2 prime, and let 1 less than or equal to D and E both are less than phi of N, such that D into E is congruent to 1 mod P minus 1 times Q minus 1. Okay. Now there is a condition. See, all these are, if D is less than 1 by 3 and raised to power 1 by 4, then D can be calculated quickly in polynomial time in log n, actually, So low exponent attack, right? So if P and Q are prime numbers, and first condition, another condition, and finally, if this happens, then D can be calculated easily. So there are a lot of, I think what I can do actually. I'm going to use again a result. Okay, maybe I can give you proof here. So since, Q square is less than P into Q, which is N. So remember, Q is less than P is less than 2Q, right? So we multiply Q on both sides. So Q square less than P into Q, which is N. So we have Q is less than square root of N. Okay. So in this case, N minus phi of N is equal to P into Q minus P minus 1 into Q minus 1 is equal to P plus Q minus 1, which is less than 3Q, which is less than 3 times square root of N. Now ED is equal to 1 plus phi of N times K for some K greater than or equal to 1. Since E is less than phi of N, all these conditions are given, right? You can see that E is less than phi of N, right? We have phi of N into K less than ED less than 1 by 3 phi of N raised to 1 by 4. Therefore, we arrive at that K is less than 1 by 3 n raised to power 1 by 4 using this result. So Kn minus Ed, these calculations are not very difficult. Kn minus Ed is equal to K times N minus phi of N minus 1, right? So this is less than K times N minus phi of N, which is less than 1 by 3 n raised to power 1 by 4 into 3 square root of N equal to n raised to power 3 by 4. So actually we arrive at this result that 0 is less than K by D minus E by N less than 1 over D raised to power N by 1 by 4. I am skipping some steps here, which is okay. This is true because 3D is less than N raised to power 1 by 4, right? So last result is there. So we arrive at something like this, okay? and now we are going to use a result. Actually, this E by N, so we need to find somehow K by 2 and K by D and E by N approximation. So here is the result actually. Result says that if X is a positive real number and K and D are positive integers, with mod of K by D minus X is less than 1 over 2D square, then K by D arises from continued fraction expression of X. Okay. So I'm sure you have not studied any of these results, right? And it will be difficult for you to understand any of these things, right? Which is okay, because that is how. So more and more, because see, if we skip a lot of results, I mean, so I mean, the flavor is like this only, right? So now, of course, it requires a proof. What is continued fraction? First of all, you should know. So I'm going to show you an example actually, right? How these things are calculated. So the job is we keep on iterating K by D, and with actually try to find that X, from that continued expression of continued fraction expression for X actually. Okay. So because you see, this inequality is something like we have here, you see, K by D minus X. So X is something like this here, okay. So we need to estimate this value. So let me show you. So I'll tell you the method actually. What is the method here? How this inequality is used here. So we know that K by D arises from the continued fraction of E by N, right? Because that is what we are going to use here. This, we are going to use this result, and we already obtained this, right? So how do we do this? Okay. So first, step 1, compute the continued fraction of E by N. So after each step, you obtain a fraction A by B. It will be clear by an example actually. Then what you do? Then you use K is equal to capital A and D is equal to capital B. So these values I am approximating with these continued fraction value, A and B, the first step, and check what happens, that C is equal to ED minus 1 by K. Why this is? Since ED is equal to 1 plus phi of N times K, if you remember, right? Okay. So third, if C is not an integer, it may happen that it is an integer, or it may happen it is not an integer. Then go to the next. Go to next value. Okay. If C is an integer, so basically we are rejecting in this case, if C is not an integer, go to the next value. If C is an integer, then you find the roots of the equation x square minus n minus c plus 1 times x plus n, which is x minus p into x minus q. This c is here, right? C is integer, then you can find the roots. Okay. So let us take an example here. N is equal to, again, this number is very large, so don't ask me how do you do these calculations. 9, 6, 8, 1, 1, 9, 3, 5, 4, 3, 7, 9, 7. And suppose E is equal to 3, 2, 3, 8, 1. 5174542919. So for the competitive programming coders, right? Can you write down the program to compute the continued fraction, right? Of these two things. The continued fraction of E by N is, we write it like this: 0, 6, 13, 2, 3, 1, 9, 1, 36, 5, 2, 1, 6, 1, 43, 13, 1, 10, 11, 2, 19, 5. Which is some, how do you read it? 1 divided by 6 plus 1 divided by 13 plus 1, 2 plus 1 divided by 3 plus 1 divided by, and so on. You keep on doing it, right? So there's a lot of interesting work on continued fraction. So actually, so given these two values of E by N, if you can write a program to compute these continued fractions, that will be really nice thing, right? So this is required. So now when you do these things, actually I can find an value. So you can see that first fraction is 1 and 6. So what I'm going to do, I will approximate by this 1 and 6. So k is equal to 1 and d is equal to 6 in that case, right? So we are going to have, so first fraction is 1 by 6. This implies that k is equal to 1 and d is equal to 6. But d must be odd. Actually, that's a condition. So we reject this case. Go to the next value. Third fraction is 1 over 6 plus 1 by 13 plus 1 by 2. If you go here, first 1 by 6 plus 1 by 13 plus 1 by 2. That is third. Okay. You observe that this value is 27 by 164. Again, this is d, which is not, which is even. So we reject this case also. Like that, if you continue like this, fifth fraction turns out to be 1 to 1 divided by 735. But in this case, c is not an integer. You can check. Seventh fraction, 578 divided by 3511. This gives you c is equal to 19669811034951136. मैं कुछ भी लिख दूंगा, you cannot verify, right? I mean, you can write a program and verify. So one c is this root of the equation, r. You can find out what are the roots. In this case, 372648873 and 527837889. These are the values p and q. So if you multiply these p and q, you will get n. Okay. So the question is, obviously the values are quite large here, right? So, but you can write a computer program to find out these things, so you can see that n is quite large here, right? So product of these two numbers is this n. Okay. Okay, so I think that's all. We are not going to do anything else. So next time we are going to look at discrete log problem, which is more interesting. Thank you.